So this is week 2, class 2, and we're still talking on basic electricity, and this is related to chapter 2. And we said there are 4 most common ways to generate electricity. What are those? Can somebody remind me? Huh? What is that?
Sun.
Sun? Okay, that's chemical. So chemical, static, magnetic, and thermal. So these are the 4 most common ways to generate electricity. And what type of electricity generation is battery? Chemical. Because we're putting some chemicals together and we're getting electricity out of it. So the most common one that we use for electricity generation in large scale is magnetism. Conductors cut through a magnetic field, causes displacement of electrons, and that's a alternator, generator, and transformer. I'll have you watch a video that is very, very informative about how is this done. So Faraday realized that at some point, when you move a conductor like copper close to steel, you are playing with the magnetic field, and that will push the electrons through and create the wave, which we say the wave is the flow of electrons. This is what we do to supply electricity to consumers in a constant flow. We use movement or thermal energy, which in turn used to cause heat. So if we think about it, again, we said a wire made out of conductor has small flow of loose electron, and we have our generator, and the generator provides waves of electrons. These waves move and cause electrons to flow. Some of them move in a single streamline, and that's direct circuit, and some of them move as alternative current. But we'll talk about that again in a lot of details. But what you have to know now is we are using mechanical power, such as generator, to make electricity. And how is this done? By putting 2 metals together in different direction to have them move. Yeah?
What's a transformer?
Transformer, good question. A transformer is a small device that changes power based on induction, and we'll talk about that in a whole chapter. You know this little, we used to play video games and you have a big box, you plug it into the wall, another wire comes out of it. A transformer changes electricity from either higher, lower, or lower to higher, based on winding and based on the same idea. If you ever open a transformer, what do you see inside? Coil. You'll see a coil, and I'll show pictures. So there's a coil, and there's an iron core, and it's work with induction, and we'll talk about it as well. We talked about insulators and conductors, which is very important to know. A conductor is a material that has free electrons available and can transmit electricity or electrons, and most metals are good conductors. And why is that? From last class, the last orbit of their atoms has a loose 1 or 2 electrons, so they can lend electrons easily. Insulators, it takes a lot of energy for them to lose electrons. Probably the last orbit of the atom has 4 or more electrons. And so they retard the flow of electrons. Example, glass, rubber, or asbestos, or any kind of polymers or carbon-based material. Wood is also a good insulator. It's really hard for them to conduct electricity. If you look at this cable here, what do we have in the middle? Copper is a very good conductor. What do we have around the copper? Kind of wax or plastic. It's kind of good insulator. And we have another sheathing, another insulator. So in the middle we keep the conductor, and the outside we keep the insulator. Question?
Do they bend that stuff?
Huh? Yeah, they have machines that bend it, but it has also an angle of bending. You cannot bend it more than a certain angle.
Is that a power line?
Yeah, it's a power line. It's underground power line. So important terms: voltage, And we have three things you have to think about. And you're gonna know them, just like your name, is voltage, amperage, and ohms. You don't have to remember them now, but eventually you will. So voltage is electric potential. These are all names for voltage. Voltage is also called potential difference. What does that mean? Let's think of voltage as weight of the water, pressure of the water. So if you have water in a tank in the roof, does it have a lot of potential? Yes, it has a lot of voltage. So voltage is the amount of the flow or power in that water. So potential difference, if you have two pots, one of them high, one of them low, and you connect them together, what happens? The water in the high pot will go down to the other pot until they equalize. So there's potential. Potential means there's difference. And that's what we're doing in a battery. There's different electric potential. It's also called electromotive forces. That's also voltage, field of force, or electric pressure. These are all terms for voltage. So if you see these in the book, they all mean the same thing. So when you think of electric pressure, that means one object has more electricity than the other. So they move. The reason that we have 110 volts and you connect the equipment to it, the equipment has no voltage. So the voltage will flow from 110 to the equipment. What if you connect an equipment that generates electricity at 110 to 110? What will happen? You have a spark because you have pressure and pressure together, so they will hit each other. And try to get the analogy of electric flow and also water flow. So, electric potential again, there's potential between the two. If you think of a battery here, there's potential difference between those chemicals when they are connected. And what happens is when you complete the circuit, the flow will go from the negative through the light bulb. The light bulb will consume some, and it goes back to the battery. Same thing with the generator. So the generator and the battery, they all have electric potential and they have voltage. If you buy any battery, it has the voltage on it, right? 1.5 volt, 9 volts, 4.5 volts, and that's the potential between the two electrodes. And always you need complete circuit. Otherwise those two electrodes are not touching. Any questions so far? These terms, once you start using them, they will make more sense. Current flow. So first thing we had the voltage. Which we can say electric pressure. If you have your garden hose connected to your house with a faucet and you turn it on and it's very slow flow, what does that mean? You don't have enough pressure, you don't have enough voltage, it's not going to flow as much. However, the amount of flow that comes out of the hose, that could be compared to the current. So current is the amount of flow. So the power, again I go back to the garden hose. The power in the hose, that's related to the pressure coming from the municipal water, guys. And the speed of how this water is flowing is at the current. So you can have a lot of pressure but not a lot of speed. A lot of speed sometimes, not a lot of pressure. And third thing is we have is the resistance. Resistance. Going back to the garden hose, what is your resistance? The hose has a resistance, which is smaller or bigger. What if you put a nozzle on it? The nozzle changes the orifice. Small orifice, I mean high or low resistance? High resistance. High resistance means more current, the water will go further, however it has less pressure. Make sense?
The pressure, this is the pressure back behind the,
Yeah, to get backed up, but you have more flow, it goes further. Question, yeah. Huh? Yeah, like a nozzle. If you have a garden hose, you put a nozzle on it, and you change the size of it. When it's smaller, it will go further, but the pressure gets keep backing up. You can feel the pressure in it. So think of the voltage is the pressure, and the resistance is the office, and it's going further. So this is a small analogy. So we have two types of current. The current can go in a flow directly. It's constant supply. Current, and that's direct circuit. Or it can travel as a wave, and that's alternative current. So this is DC, and if it goes in a sinusoidal wave from between plus and minus, that is AC. And what do we need to know? We need to distinguish between what is AC power and what is DC power. In a battery, think that's AC or DC? If you don't agree, raise your hand. Why do you think it's not AC?
Because you said a battery, and I know on batteries there's positive and negatives.
Yeah.
So,
So directly,
I guess.
you get only negative the whole time. You don't get negative and positive. So it's direct supply of negative electrons all the time. So that's direct current. DC. So all batteries will supply you constantly. So with a battery, you have two poles, plus and minus, and the flow comes from the minus side directly until the whole battery is depleted. So that's direct current. Constant supply, the same charge the whole time. Make sense? What would be an AC? AC, that's something you find in your household receptacle. That's AC. And that's why sometimes it does not matter if you change the polarity, because the AC will give you plus and minus, like a wave. So you can switch the plug back and forth, and it's going to work, right? Have you ever experienced that? Not all equipment are sensitive about polarity. So you can switch it and it still works. With DC, if you switch the current, things might not work, and sometimes you might reverse the direction of the movement. We'll talk about that in a whole chapter again. So the unit of voltage is volts. So an Italian scientist called Volta. The current is amps. Amps or ampere, the scientist ampere. And resistance is ohm. Again, another scientist whose law we're going to talk about a lot, Ohm's law. So these are the major units of our three components: volts, amps, and ohms. Write these down, but again, we're going to talk about this more and more later. So resistance, again, they oppose the flow of free electrons, and the higher resistance, the less flow you get. And you want things with low resistance, that's in our favor because we don't have to generate more electricity. However, most equipment, what we call loads, like a light bulb, an AC, a motor, they have to use that power, and therefore they are considered to be resistances. So we have here current flow, and this resistance will oppose the current flow, and eventually you get some power consumed. So think of it of obstruction of the flow.
so that little thing looks like a headphone,
That's the ohm. It's the ohm symbol. So this is resistances. Electric power. Oh, it's getting complicated. Fine. So again, I'll spend the next entire week talking about Ohm's law and electric power. So electric power is what you pay for at the end of the month. If you look at your electric bill, it will say kilowatts. And if you notice, when it comes to watts, watts has a time component in it. How much do I consume per second, per hour? So, the rate at which the electrons do work, are consuming this power, measured in watts, and power equal voltage times amps. It has other units, but mainly for electricity we pay with it everywhere, universally with kilowatt hour. How much you consumed for 1 hour. So if you look at your bill, they charge you for kilowatts. So whatever resistances you have in your house, it's how much you consumed, and I'll show you how to calculate that and how to translate that into money. Question? Louder? Yeah. You'll see how the bill is calculated, and you can predict how much you're going to consume based on your equipment. So you know the voltage in your house, right? What is the voltage in your house?
220,
240.
210.
Most of the inside 110.
110.
110,
Yeah,
115. You know your voltage is gonna be does not change that much, and you can know the resistance for each of how many amps does every equipment runs, and you can know how much watts. You add all the watts, and you see how much you pay for the kilowatt hour. How much is the average kilowatt hour in Massachusetts? Yes, 15 cents. This is eventually gonna add up, and you're gonna pay for it. So, when you buy the equipment, it should label on it what is the average, or it should label on it something called the watts. And sometimes they try to be tricky, and instead of paying some watts, and sometimes they'll say power. And I want you please to go and look at some equipment, and they say it's VA. They don't give you watts, VA. What is VA? Voltage times amperage. So you tell this is VA. What is VA? Is voltage times amperage. So if you look at any equipment, you'll see that. Look at this. I'm going to show you.
Yeah, go ahead.
It should show in the battery somewhere. I'll take out the battery, but I don't want to.
That's not good. That's our own.
I'll find some equipment and show you the power on it. So the point being is every equipment has to have some kind of consumption on it. But start paying attention to these things. It will make a lot of sense.
In the UK, is it the same one?
110?
This
No,
one?
I think 220. In Europe, in Europe it's 220.
I mean, it says a lot of A's in it.
Okay, so if you look at this battery, now we can translate and decipher this a little bit. So you're gonna develop some awareness of these little symbols they always have. So this battery is DC volts, 5 volts, and it consumes 1 amps. That's the input to charge this battery. Output DC 5 volts, 1 amps, and sometimes 2.1 amps max. So it will fluctuate based on the use of the computer. And this is the capacity. This is how much amperage it consumes. 10,000 milliamps. What is milli? It's a fraction of 1,000. Millimeter, 1,000 of a meter. Milliamp hour. So these things will start to make sense to you after a while, and you understand how do they function. And please try to pay attention to these things. It makes a lot of difference, and it makes up for a good and bad technician. You have to read the voltage. What is your consumption? If you have an AC that is 220 and you plug it into 110, it's not going to work. You have to understand the hot legs and the neutral legs. You have to understand the phase. We'll talk about the phase later on, which is single phase, double phase, and 3-phase equipment. Well, mostly for household residential stuff, it's 1 phase, but we'll talk about that so you'll be able to distinguish and know what it means to have a phase and what it means to have triple phase. So, all right, which power is being used at a specific time, measured in watt hours. So watts usually have a second component in it, but they give it to you in hour because it makes it more easier to calculate. Ohm's law. Ohm's law. Let's talk about that a little. Maybe it's a little bit too much. I'll do Ohm's law on next week. What do you think? So now you know the units. Can you please do me a favor and check the chapter? Try to skim through it. I'll spend the whole week on Ohm's law and its calculation. For now, I want you to remember three things: voltage, amperage, and resistance. Read those, try to understand them. These are the very, very basics for electricity that we have. And I'll let you think about it a little bit. Let me touch base on it a little bit. Calculation, too much. I'll just touch base on it, then we can do the questions together in the back of the chapter or something else.
Yeah, that does my phone, everything.
So the relationship of Ohm's law, we have two laws. Write those down. I will talk about them again next class. So this is Ohm's law. What is V? Voltage. Volts. What is amperage? That's current. And this have different symbols, by the way. So is this. So make sure that you know the variation. It could be P, it could be potential PE, or it could be what else do we have? Sometimes capital A and something else probably in the book. Current is C. Sometimes they put I for symbols depending on the book or the industry. And this could be just a symbol omega, ohms, or just resistance. When in doubt, just write it down. Voltage on top, resistance, amperage. Okay. The way we understand how to use this law, very, very, very simple. So you put a triangle on, and from top to bottom you divide, and from side to side you multiply. Sounds very ambiguous, no? If I want to find the amperage, I'll cover the amperage, and what do? I divide the voltage by the resistance. That's it. If I want the resistance, I'll cover the resistance, and I'll divide that voltage by the amperage. If I want the voltage, what do? Multiply those two together. So the first thing you do when you get any problem with Ohm's law, you write this triangle, and you see what you want to find out, you cover it. From top to bottom, you divide, side to side, multiply. We'll do a lot of examples about that, but it's very, very, very essential. So, two things you have to remember. Write the triangle, voltage in the top. That's Ohm's law. Second thing, make sure the units are consistent. If you need volt, amperes, and ohms. What if you get milliamperes? You convert that to amperes. It's not going to be this for our field. We only deal with amperes, ohms, and voltage. So that's going to be Ohm's law. I'm going to write it that board. I'll leave it there for you so you don't forget. Put it over here. That's going to be Ohm's law. It will stay here the entire semester. You can tattoo it. You can put it in a card. You can put it, do whatever you want with it. But this is it. You're going to use it for this semester, next semester, and the entire career. That's Ohm's law. What do you think? Hard? Cool. So I'm going to keep this here for you to glance at if you need it. This is Ohm's law. There's another law. which cover the rest of the electricity. So what, we talked about four things, right? Voltage, amperage, resistance, and what is the fourth thing that you pay for? Power. And power is in watts. So, the power law, same thing in the triangle. So power with V, volts, and here we have A. So this is amps. No. And volts. Yeah. So power. Again, same trick. Multiply, divide. So, as Cass said, there's no resistance. We need to have to find the amps. But if you don't have the amps, we go back to the Ohm's law and find the amps. Voltage is always easy to find. You go on here for voltage. Resistance also is easy to find. You can go on here the resistance. And these are the two laws you will need to do most of small little problems that we have here. But we'll spend some time next week talking about the power law and how to measure that. So they have the same formula in the book, but they give you all the alteration. And as you see, they put E as a symbol of voltage, which is the same thing, and they use a circle, like a triangle. Do a circle if you want. And again, in the exam, you can put this in a cheat sheet and bring it with you. I don't care. I don't want you to remember these things, even though it's very easy. Power in the top, voltage in the top, this in the bottom. But it takes a few practice to get it done. And of course, there's a lot of variation, but if you know how the triangle works, it should be easy. This formula is so confusing, so I don't want you to remember that. Which is basically a derivation of combining those two together. No, let's take our time to it one by one. I get confused with them, with the square root and all this nonsense.
No square roots.
Huh?
No square roots.
No square root, no problem. We're not gonna do that, okay? So if you know these two very well, it should be enough. It's a shortcut. No, I don't want a shortcut. Let's just do that. Very often. Let's focus on that. We'll do a bunch of exercises on them. And it's very, very essential for many reasons. It will enable you to do good troubleshooting. And if you go work in any company, knowing the Ohm's law will help you understand what is the voltage you're supposed to expect, what is the power you're consuming, and a lot of electrical problems will be driven from those two laws. Let's do a quick example. The last few minutes. If the voltage is 120 volts and the resistance is half an ohm, what will be the current? What is with this? It's the bit. 60 amps. So guys, so what am I looking for here? What is that required?
Look for A.
Yeah, excellent. What is A?
Current and
Yeah, how do I calculate that?
B divided by R.
Excellent.
Right.
You passed the course. That's enough. I'm happy now. That's it. That's it. So this is the amperage, beta over R. What is the voltage? 120. What is the resistance? 0.5. Gonna be 240 amps, which is ridiculously high. But this is just an example to practice the math. So we'll do a few of those as we go along, and hopefully it will stick. And I'll spend at least a week on Ohm's law and power law. And please, if you have any issues with it, if it doesn't make sense, let me know. We will try to recap on it as much as we can. One more example. If the voltage, this is the same one, So, if the voltage is 220 and the resistance is 0.5, what is the current? It's going to be the same thing. 240. Resistance is 1 again. It's going to be high.
Wait, it's not 240, it's 220.
220? Okay. Somebody's awake. 440. Ridiculously high, but at least the math is correct. Okay. This PowerPoint is online. There are a few examples in the book. And let's see what they go through. They dive into the laws, and there's plenty of examples here. One thing I need to touch base on, I think they skipped. It's the law of electric charges. Law of electric charges. Opposite attract, different same will repel, opposite will attract. So positive will cause things to repel, and negative and positive will attract. And that's very important because it will help us understand some static electricity and some laws of doing a complete circuit. Propulsion of two positive charges, negative charges will also propel each other, and different charges will attract. Okay, so I will end the class here.